Hello everyone, thank you for joining me for today's video. Mr. Ish here. I want to continue the topic from the previous video, conic section regarding parabolas, by presenting just some practical applications. Here I've drawn a little picture of a parabolic dish. You're familiar with this in terms of satellite dishes or receiving dishes. So let's look at an application with regards to a parabolic dish. And all parabolic dishes and cross sections are parabolas. Let's look. If you look at this type of a dish and you just translate it into an x and y axis, but in an upward directing parabola, making it look something like this. And of course, these lines could continue to infinity. But in terms of practicality, no dish extends infinity. It has a certain endpoint. Let's define an endpoint over here. Let's call this, we're 30 units this direction and we're 10 units up. So we're 30 here and we're 10 here. So this endpoint will be 30, 10. Alright, this endpoint is 30, 10. Likewise, this one will be in the exact same dimension but on the opposite end, minus 30, 10. So looking at this, just by looking at this, we are seeing it's an upward parabola. X squared is equal to 4py. How does the shape of a parabola change or affect the focal point, which is where this receiver would lie? So that's what we want to take a look at. And we want to look at that question in terms of the p-value, because the p-value will determine the focal point, which is where this receiver will lie. So if you consider a 30, 10, and 30 could be 30 feet, 30 meters for those very large dishes, or it could be inches or centimeters, whatever your units are. If you're looking at something 30, 10, 30 this way, 30 this way, so you know the entire dimension here is 60, alright? But let's focus on the 30, 10, and let's use the 30, 10, my x and my y, and let's calculate for that y. When we put 30 in place of x, we get a 900, because 30 squared is a 900. Then we have a 4 multiplying with the p and multiplying with the 10, which is a 40y. Let's calculate for that p. And I'm going to use the calculator here, so we'll get 900 divided by 40 and we'll get 22.5. And as I said, what are units? Meters, feet, centimeters, inches, whatever. Okay, so my focal point will be 0, 22.5. Now if you think about it, if you're 30 units up here, 22.5 is kind of up here, focal point. But if you're talking about a large receiver, 22.5 feet, meters, that's pretty high. So how does this focal point or the position of the receiver change as the shape of the dish changes? Let's jump on to another scenario. A similar dish, again having the same dimensions of y, because we're only going to change the x dimensions. Now we have something a little more narrow. We're looking at 20, 10. I'm going to draw it on the other side, but I want to notate it. But this would be minus 20, 10. But see, now we've made the parabolic dish more compressed. How does the focal point change here? Let's plug everything in the original equation, x squared 4py, which is representative of an upward parabola with a vertex at the origin, and calculate for that p by substituting my x and my y value. X here is a 20, 20 squared is a 400. And then we have a 4 multiplied by p multiplied by y, which is a 10. You see I've kept the y values constant, which is fine. Keep something constant and affect only another dimension. We're affecting x only. And let's solve for the p over here. We'll do 400 divided by 40, and I believe that would be 400 divided by 40 would be a 10, right? 400 divided by 40? Yes, 10. My mind was slipping with that one. So the focal point here would be 0, 10. You see, as we've compressed the dish, our focal point has come closer. And again, the focal point is the position of this receiver. See, we brought the receiver closer to the dish. So maybe the receiver is now over here. Let's look at one more scenario using the same dimensions but changing only the x. Here we've compressed it even further. Now our dimension here is a 10, 10. We're keeping the y value the same in all, 10, 10, 10, but we're compressing the dish in terms of its steepness. And we're making that x value 10 over here. Let's calculate again for the focal point, the position of that receiver. We'll plug in 10 squared is 100, and then we have a 4 multiplying by the p, which we have to calculate, multiplying by that y value 10, And here our p-value would be 100 divided by 40. I believe that's a 2.5. 100 divided by 40, yes, that's a 2.5. P-value of a 2.5, which means my focal point, my new focal point will be 0, 2.5. And where will that focal point be? All the way down here. You see our focal point was quite up towards the top of the dish. And then by compressing the dish, we're bringing the focal point, the receiver, further down. Imagine if this was like a very large number. The focal point of the transmitter would have to be quite far up. So how is this practical in terms of any value? Well, there's a trade-off which is involved over here. Dishes which are pretty broad have to have a receiver pretty high. But one of the benefits of having a broad dish is you can receive more transmission. So yes, you have a greater quantity of transmission falling on your dish. You can collect more transmission because you have a broader dish. But the cost of a broader dish is your resolution may not be good, or the quality of that transmission may not be good. As you bring your dish, the parabolic dish, as you compress it, you're able to bring your focal point, your transmitter, closer to the base of your dish, and your resolution and your quality will improve. But again, here the trade-off will be that the quantity of transmission you can receive is decreased, simply because the dimensions of your dish, the left to right dimensions are smaller. So that's just an example here in terms of parabola. Changing the width of the dish will affect the focal point, and that focal point represents where your transmitter will be. Let's look at this other example of a parabolic application. A suspension bridge. A suspension bridge is representative of parabolic curves, but actually multiple parabolic curves. If you look at the bridge, it could continue on outside the board and you'll have multiple parabolic curves. But we're only looking right here at the central portion right over here. If you look at this central portion right here, it looks like an upward facing parabola. A suspending cable suspending the underlying bridge. This right here is my bridge, and these are like the bridge towers which support the main cable. The main cable has these vertical lower cables that actually hold the weight of the bridge. If we want to calculate the equation of this, which is what engineers will do anyways when they're designing the bridge, we would actually start by imagining this line over here, the actual road, represents your x-axis. Then what you would do is just draw a vertical line right in between, which would represent our y-axis, and suddenly we have an origin over here. And now the parabolic curve has been split by this line of axis into two equal sides. And again, we have an upward facing curve. So we know our equation is x squared is equal to 4py. There's really no guesswork involved over here because they know what the length of each of these road segments are. And let's come up with some numbers. If supposedly from the distance from this one tower to this other tower is 50 meters, I guess meters would be a sensible term for a bridge, then we know from the origin to each of these towers is 25, right? We know that because 25 plus 25 will give you that total distance of 50. We also know, the engineers also know how tall the tower will be, and you're always measuring it from the base of the road. From the base of the road to the height of the tower, imagine it could be, this is not drawn to scale, it could be, let's say 20. Because normally towers have to be pretty tall to hold the weight of the road. Just by knowing these facts, we already know this coordinate over here is going to be, it's always x comma y. It'll be 25 comma 20. 25 representing the x, the length, 20 representing the y, which is the height. So what do you have? You basically have a vertex as the origin and you have a point on the curve. You need nothing else to determine the value of p over here. But here we're not determining the value of p for any focal point because the bridge is not going to have a focal point. We're only using these values to determine the equation of the cable which is in the shape of parabola. So let's plug in the values. We still have to calculate that p to determine the final equation. Here's my x, here's my y. Let's plug them in. X squared, which is a 25 square. I think 625 is equal to 4 times p times y, which is a 20. So we'll have 25 square, I believe 625. So 625 is equal to 80p. Remember, we're determining the value of p because we're going to use that to determine the final equation. We're going to divide 625 by 80 and we get an answer 7.812. 7.8125, which is fine. We can have a decimal answer. Let's take this 7.8125. We should be plugging it right in here. And let's erase it. You want to plug it into your final equation, your equation form. So you get x squared is equal to 4 times 7.8125, multiply that by 4, and we get 31.25y. So this is the equation of the cable, this main cable right here. That's the equation of this curve. But why is knowing this important? It is because once you know the equation of the cable, you can order the sizes of these vertical cables. If you know how far each of these cables is being placed, you know that beforehand. You know what the length of these cables will be. Imagine if this cable is basically, let's say 12 units or 12 feet away from here. So what's going to be the height of this vertical cable? It's easy. You know the x-axis is 12. You know the equation. You're going to solve for that y. You'll plug in 12 right over here in this x squared, and you'll solve for that y. That y will represent the height of this cable. So let's do that. Let's plug 12 in place of x. 12 squared is 144 is equal to 31.25y. Solve for that y. 144 divided by 31.25, and we get 4.608. 4.608 meters, feet, whatever it may be. This cable right here is going to be 4.608 units tall. And we know that's a sensible answer because as you see the curve is going upward. If you went all the way up to 25 over here and you calculated the height of this tower, you should get 20. And let's do that. Let's put 25 and squared and divide by 31.25. So we're going to 25 square and we'll divide that by 31.25 and I get 20, a height of 20. So we know our equation is good. And if we use this equation in terms of any of these horizontal distances, we can calculate the height of any of these vertical supporting cables just because we've determined the equation of this parabolic cable. So that's the end of this example. Let's look at this other example. It's not a practical application, but it's also a scenario type of question you may easily see on any test. Here you're given a focal point and a directrix, and you have to just determine the equation of this using the basic equation form. And you have to determine what type of equation form you have to use. If you're given the focal point and the directrix, you know that the vertex is somewhere in between. The fact that you have a directrix, which is a vertical line, tells you we're looking at a right or left parabola, because an up and down parabola would have a horizontal line directrix. And you also know that the focal point must always lie within the curve of that parabola. So we know we have a parabola that will point in the direction of the left, which would have the equation form y minus k whole square is equal to minus 4p times x minus h. Minus is essential over here because we're pointing towards the direction of the left. The only goal here, which is perhaps the most important part, is to determine the vertex h comma k. And we can do that by determining the middle point of this focal and a point which would fall right on this directrix. If this directrix is x equals 8, we know the x-axis value here is 8, and we know already the y value going across is 8 comma 2, and this is a 2 comma 2. So what's the midpoint of these two? Think back to the midpoint formula, x1 plus x2 over 2 comma y1 plus y2 over 2. Take the x-axis values, add them and divide them by 2. 8 plus 2 is a 10. 10 divided by 2 is a 5. Y values never change. So my midpoint here is 5 comma 2, and that is my vertex. And the parabola faces in the direction of the left. Yeah, the direction is not, it's not a very clear drawing because this curve should have been right over here. But imagine it fell on that point. So I have a vertex h comma 2, focal point 2 comma 2, and a directrix x is equal to 8. All we have to do now is calculate the equation, and we know what our p-value already is just by looking at it. The p-value is always the distance between the focal point and the vertex, or the vertex and that directrix, and it's a 3 on each side, because a 5 minus 2 is a 3, and an 8 minus 5 is a 3, and I'm only looking at the x-axis values because I have movement along the x-axis values. The y value stayed the same, so the p-value here is 3. Let's plug in these items. We have our h and a k, which are vertex. We have the p of 3. We're just plugging in these items. So we have y minus k, which is this right here. Here's my k value, 2 whole square is equal to minus 4 times p, which is my 3, which I can see clearly from my graph, times x minus h. H here is my x coordinate of that vertex, x minus 5. We'll be a little fancy overhead. We'll solve this all out. Y minus 2 whole square is equal to minus 12 times x minus 5. Minus 12 times x minus 5. Let's open this up for our final form, which will complete the equation. Minus 12x plus 60. So this here is the equation of this scenario. Focal point 2, 2, directrix x equals 8, vertex 5, 2, p-values of 3, a left directed parabola. Thank you for joining me for this practical video over here. Please like and subscribe and share. Have a great day. Thank you. Bye.